we define the étale fundamental group. So X is we are connected scheme. X bar is a geometric point. And then to such data, we associated profinite logical group, profinite group, the pi1 of X with base point X bar. So this construction is functorial in the following sense. If you recall that this group is has a property that finite pi1 sets that this category is equivalent to the category of finite étale covers over X. So the information about this group can be translated into information about finite étale covers and vice versa. Now, so this construction is functorial in the sense that a morphism F from X X to X prime, let's call it F, and you have a point, a geometric point X bar. Then you also have geometric point of which I will denote f of X bar, geometric point here. And so this diagram gives rise to a functor between category of finite étale covers of X prime to finite étale covers of X. Which takes a cover y over X prime to y times X over X prime. This is a finite étale cover over X. Let's pull back. So you get a functor, and this functor commutes with the fiber functor, finite sets. So this is fx, f of X bar, and this is f X bar. And therefore, it gives rise to a morphism from pi1. So every automorphism of this functor gives rise to an automorphism of this. So this induces a homomorphism, continuous homomorphism of the étale fundamental groups. Okay? So we have functoriality. Now, next, I want to discuss the dependence of the formation of the étale fundamental group on the choice of base point. Base points. Well, we know in topology that so if you have a topological space then, well, every connected topological space, then for every point you can define the fundamental group. Those groups are independent of the choice of base points up to non-canonical isomorphism. In fact, to specify an isomorphism, you have to choose a path, a homotopic class of paths from one point to the other, right? So if you have 2 points x and x prime, then and if you choose a path, then for every closed loop here, you can associate a closed loop starting at based at point x bar prime. Namely, you go this way, go around this loop, and then go back. This this induces an isomorphism between fundamental groups, which really depends on the choice of this path. If you choose another path, right? So it gives you a loop based at point x prime. The isomorphism gets conjugated by the class of this loop. So we would like to see a similar, whether there exists, whether we have a similar picture in break geometry. So here is the lemma. So this turns out to be a very general statement. So, okay, maybe before I give a lemma, let me give a definition. So suppose I have a category, a functor from this category C to finite sets is a fiber functor if pair is a Galois category. Okay? And then we have a lemma. Any two fiber functors F1, F2 from C to finite sets are isomorphic. So I recommended to think about this this problem, this lemma, for the lecture. So so if you did this, then the proof will be, well. So I'm sorry for repeating the argument. But it will be short. So so we already know that any. So let's consider C with F1. So it's a Galois category, and we know that Galois category with this functor equivalent. So C with F1 is this pair is isomorphic to the category of finite G sets with forgetful functor. Там была такая теорема, что если у нас категория Galois, то значит, ну как строится G, во-первых. G это автоморфизм F1. Значит, ну, тогда получается функтор из c ну, в конечное g множество. Просто f1, вот у нас есть функтор f1. Да, да. Да, а дальше такая теорема, что если эта пара — это категория Гуа, то этот канонический функтор, он является эквивалентностью категорий. Мы ее так частично, но я сказал, что мы ее, она важная теорема, но она чисто такое категорное утверждение, мы ее начали доказывать, и я сказал, что, значит, ну, это, с одной стороны, ну да, это, конечно, самое сложное, но я это хочу использовать. Вот. Да, и без этого было бы сложно. Вот. Very good. So we know this. Of course, we could construct, we could replace F1 by F2, and then a priori I would get another group. And we want to show that these two groups are isomorphic, right? Okay, so we have, so I will still call it F1, maybe. And then we have, from this category, so we have another functor, F2. Да, да, да. Нет, теперь, значит, у нас как бы f1 стал просто забывающим функтором, а f2, ну, какой-то функтор отсюда.
Мы хотим доказать, что категория была два основных функтора изоморфа.
Да.
У нас категория была эквивалентна вот этой, поэтому можем просто доказать, что любой файбер функтор изоморфен забывающий.
Да. Ага. Хорошо? А чем вы недовольны, Лиза? Хорошо. Okay, so what is the idea? The idea is that F1 is almost a representable functor. Almost means that it's representable, it's pro-representable. I will. It's inductive. It's inductive limit of representable functors. So F1, what is F1 of x? So F1, again, is a forgetful functor. Is it representable?
Но это кома из G.
G, прекрасно. Но только G не объект моей категории.
Ну, значит, по пределу.
Okay. So this is, I will write it as co-limit, and I will take our co-limit over all open subgroups. Open in particular is finite index, normal. So this is just x, the underlying set x. And this is, I want to write it, x as co-limit of invariance under all, where H runs over all open normal subgroups. I'm using the destabilizer, so X is equipped with a continuous section of G. That means that stabilizer of every point is open. It means that the whole X is stabilized by some open normal subgroup. So this is clear. And now these functors are representable. So this is morphisms in my category. Category C, well, category functors. yeah, sorry, in category C, G mod H X, right? Agree? Because this is precisely invariance. So, and now I can use Yoneda lemma to conclude that morphisms from F1 to F2 so far, well, okay, for every F2, so this F1 is co-limit of representable functors. It follows that morphism from this is the same as inductive limit. Sorry, not inductive, inverse limit. With the same H in G of F2 of G mod H, right? Agree?
So we use that limits and co-limits as a category of factors are completely pointless.
Yes. So, and now I claim that this limit is not empty. Why is that? And here I have to use that F2 is a fiber functor. So, well, so this category I'm taking limit over is what's called a directed category, right? So for every two open normal subgroups, there is a smaller subgroups that contain, which is contained in both of them. So it's a directed system, right? And so if another property that I need is that if so if you have H as a subgroup of H prime, then of course I have a map from f of G mod H to f of G mod H prime, right? And this is surjective because the functor is exact. So you see, I am applying a functor to a surjective map, epimorphism in my category. And if every fiber functor is exact, after all, it's isomorphic to the forgetful functor. By the way, what is a epimorphism in a category? Abstract category.
То, что можно сокращать.
Да, так что абсолютно верно. Okay. So an exact functor, in particular a fiber functor, takes an epimorphism, so a surjective map, to epimorphism. So I have a directed inverse limit of something, of sets, and well, all the maps here are surjective. And then there is a set theoretical statement that such inverse limit is non-empty.
I think the statement is wrong, and counterexample is n, and left shift.
What is left shift?
No,
The
the
natural.
sets are finite.
Finite sets, right?
If they are not finite, it's
Yeah, fine. Yeah, finite sets. Thank you very much. Finite. Yeah. Thank you. Okay. So if you believe to this statement, which I will urge you to do, then so we show that this is not this is non-empty. And similarly, morphisms from F2 to F1 non-empty. Right? We can just replace the roles of F2 and interchange the roles of F1 and F2. So F2 is also becomes a forgetful functor for some probably other group G. So this is non-empty. So you have a morphism from F1 to F2. And you also have a morphism from F2 to F1. And I want to show that the composition is an isomorphism. And but morphisms from F1 to F1. So we get, this is, say, alpha, and this is beta.
Когда мы говорим, что предел не пустой, но мы еще используем, что F2 от факторов не пустые, да? Это просто...
Да, что точность используем. Да, совершенно правильно. И конечные и не пустые. Понятно. Спасибо большое. Спасибо. Okay, so now I claim that every morphism from F1 to F1 is actually an isomorphism. Okay? In order to do this, let's just use the same computation. So you get a limit over H of G mod H. But G is profinite, so this is G. And this is automorphism of F1. So this implies that alpha composed with beta is isomorphism. And this completes the proof. Okay? Is there a simpler argument? Is there a simpler argument? Да, Дима? Да.
Что для каждого объекта там можно придумать.
Да.
Связанный объект, что силуэт морфизма из этого.
Да.
Для обеих слоев можно это построить и получаем отображение между слоями.
Нет, но почему если сейчас? Ну а почему есть отображение между представляющими объектами? Ну, надо доказать, что есть отображение, но даже если F1 и F2 представимы чем-то.
Нет, там получается, что...
Можно явно построить, чем они представимы.
А чем?
Там будут произведения.
А чем?
Объект, там, сложили его там в единицы связанных множеств, перемножили эти все множества.
Ага. Ну, a little bit, well, you see, the representable object deserves, the object that represents this fiber functor deserves to be called the universal cover, right? So, like in topology. So you have the fiber functor from the category of covers to the category of sets. Is it representable? all covers.
Well, then yes.
Yes, by what is the object it's represented by? The base space is good enough, right? Otherwise, we don't have. It must be connected and locally contractible. So what is the so the fiber functor? What is it represented by? What? Universal cover, right? Morphism from a universal cover. Yeah. Right. We want to show that any two universal covers are isomorphic. There is no canonical isomorphism between them. So you have to do some choice.
Не, у нас в теории нет границы,
So what?
не говорю, что
Нет, но проблема, мне кажется, что тут в том, что поскольку мы хотим построить нечто, что совершенно не единственно, нужно использовать какое-то утверждение из теории множеств, какую-то лемму Цорна. Вот как доказывается вот это вот утверждение про пределы? Да, поэтому без нее как-то не обойдешься. Мне не кажется, что есть очень простой по этому аргумент.
В частности, из этой леммы следует из этой леммы единственность алгебраического замыкания для поля.
Ну, да. Good. So, which is also kind of, I think it uses some, also a version of Zorn lemma, right? Or maybe just directly. How you prove the existence, uniqueness of algebraic closure?
I believe there is an example, if axiom of choice fails, then there is a field which has two non-isomorphic algebraic closures.
Mm-hmm. Okay, so we have we proved the so in particular we have пронётировость? Нет, не нужно. Okay. So we have sort of an abstract isomorphism between profiling groups. It means that, I shouldn't say abstract, non-canonical isomorphism between the such fundamental groups, and it's well-defined canonical up to composition with an inner automorphism. Right? So this is important. So why it's canonical up to composition with an inner automorphism? Well, so choice of a base point determines the fiber functor. So any two fiber functors are isomorphic. So you choose this isomorphism, which is unique up to, well, it's not unique, but it's choose an automorphism. Two isomorphisms differ by an automorphism of a fiber functor. So this gives you the automorphism you want to conjugate by, right? So, okay, is it clear enough? Good. So now let's do a sample first computation of the Tal fundamental group. We have a very general definition, but it's extremely difficult to compute a Tal fundamental group. So let's take first x equal to spec k. well, I need X bar is it's going to be a morphism. So I choose an algebraic closure. This will be my base point. So, so I claim that so what is my functor? Well, so first of all, what are finite covers, étale covers over spec K? These are finite dimensional algebras. So spec A, spec K. So this is finite étale X, such that A is product, finite product of fields where Ki is a finite separable extension. That's by definition. So what is my fiber functor? Well, it takes so I identify this category with the category opposite to the category of such algebras. So this is going to be, by definition, just morphisms from K points, so from A to K bar, right? Which is the same as morphisms in the category of algebras. So, for example, if A is just a field, I look at the set of all embeddings of my field K into K bar. So this is the same as morphism from A to K to the separable closure of K. So, and of course, the Galois group K sep over K acts here because it acts on this field. So we get a map from Galois group of K sep over K to the automorphism of my fiber functor, which is pi 1. And the claim is that this is an isomorphism. So how you do this? Well, you use the same trick. You filter, well, you represent this fiber functor as an inductive limit of representable functors. Namely, so f x bar of A is limit over all say, Galois extension, K sep, and this will be K prime, and this is Galois, finite, morphisms from A to K prime, right? And then you use unit lemma to conclude. Okay. Use this. Okay, so at least we can relate the Tal fundamental group with something familiar in this case. And let me give you another example. So suppose I have a scheme, say X over Fp, or maybe over Fq. Okay. And then suppose I have a point, X in, so X is a point, spec Fq mapping to X, Fq point. Then this gives rise to a homomorphism of Tal fundamental groups. One is this, and another one is pi 1 Tal of X. Well, this group is easy to compute because it's Galois group. Galois group is very difficult to compute, but not in this case. So in this case, it's D hat. Moreover, it has a canonical topological generator called the Frobenius. Which is just takes an element and raises this power. Maybe I should take Q. And therefore, we get, well, I would love to say that we get an element here by taking the image, but this will be an exaggeration because I deliberately do not fix here base points, right? Because I really want this point vary. I don't want to keep track of base points. So that means that my morphism, this homomorphism, is defined only up to conjugation. Otherwise, it depends on some additional choices. So get a conjugacy class.
But the induced homomorphism only exists if you take a geometric point which kind of lies over X.
Well, you need to choose, right, but I can't do this, right?
And then what you sort of want, if you take this and then you compose it with a non-canonical isomorphism to any other base.
Okay. So, but I have a well-defined conjugacy class. You agree? Class. Pi 1 Good. So you can also play this game. You can replace X by by any scheme. It doesn't matter. So you just take f point. I could, let me just erase this. Doesn't play any role. Okay? For example, you can take some ring of algebraic integers. Z adjoint square root of -5. Okay, so no, let me give you another example. That's almost everything I know how to, almost exhausted list of examples where I know how to compute the fundamental. So let's take P1 over an algebraically closed field. So what are finite et al. Covers? Well, first of all, y must be a curve, even a smooth curve. So, and let's assume that it's connected. Connected curve. Then I can compute in genus using the Riemann-Hurwitz formula. Well, Riemann-Hurwitz formula is complicated when you have some ramification. But my morphism is unramified, meaning that it's isomorphism on tangent spaces. Right? Нет, мне не нужно... Зачем нужен Фробениус? Никакого... Нет, Фробениус не является этальным. Ну да, ну просто по формуле Римана-Гурвица, so we immediately get that if this is if degree of f is d, then we know that the Euler characteristic of the base, which is d times what is the Euler characteristic of the base? What is the Riemann-Hurwitz formula? It serves that the Euler characteristic of this is equal to multiplied by degree is equal to the Euler characteristic of the total space, which is y. 2 minus this. Right? How you prove it? Well, the simplest, so that's true only when your morphism is unramified, and the simplest proof is the following. Take a rational, right? So you have a differential form that has poles at 2 points. Take its pullback and compute its divisor. Compute its degree. Genus is related to the degree. So if your morphism is unramified, so if fiber is non-reduced, so the morphism on the tangent space is not surjective, then you may kind of acquire some extra zeros of the pullback. But if not, then divisor will be just degree of the divisor. So degree of the divisor here is 2, and so if you take the inverse image of this form, its divisor will have degree d times 2, and that's it. That's complete the proof. So that means that genus, well, the d is 1. So it's a nice place. Okay, so and that means that there are no connected covers. Every cover is the category of finite total covers is just equivalent to the category of finite sets, and therefore this is trivial. Okay. Now. Yeah, so as I said, that's almost all I know how to do. Just over an arbitrary field. But so to give kind of, to get deeper results. Да, УПН, Катя, ты рассказывала, это я сказал almost, и это будет в упражнениях. Ну, да, для эпистической теории тоже можно. Но вот уже для P1 без 3 точек чудовищно сложно. Okay. So so definition is very good, but when you want to compute something, you have to use some deep, complicated machinery. So complex varieties over varieties over complex numbers, or over a field of complex numbers. Sorry. Okay. In this section, all schemes will be of finite type over C. So if I have X, I can associate to it topological space, so which is just the set of C points with usual topology. So what do I mean by usual topology here? Instead of kind of giving, let's say that if I have X and as a risky open subset, right? So it's then so the topology is defined in such a way that C points of U is declared to be an open subset. This is open. And on the other hand, this is, that's going to be a subset here. And this is closed. Where Cn, I should have written this. That's already a topological space. So where Cn is endowed not with the risky topology, but with complex topology. That's how you define, that's properties characterize topology here. Another way of putting it is the following. This is the weakest topology where certain functions are continuous. And what are these functions? So for every open subset, the risky open subset, and every algebraic function on this open subset, which we think of as a map from this guy to C, this function is continuous with a classical topology on C. And you take the weakest topology where all these functions are continuous. That's equivalent to the description that I gave here. Okay, so we have this determines a functor from the category of schemes over self-finite type to the category of topological spaces. So if you just think of a projective scheme given by something defined by algebraic equations, you simply take the same algebraic equations in complex projective space with a classical topology.
У нас получается, что U аналитическое замкнуто в C,
Да.
и при этом требуем, чтобы оно было открыто.
Ну, в X, ну да. Ну, то есть, значит, еще раз, какое множество мы называем открытым? Мы называем, сейчас, давайте так, какое множество мы называем замкнутым? Значит, множество называется замкнутым вот здесь, если для каждого U и вот такого вот вложения, если я пересеку мое множество с вот этим, то я получу замкнутое подмножество в C. Подмножество, да. Мы определили топологию.
Да.
У это афинное многообразие, а афинное многообразие это замкнутое подмножество в C.
Угу.
У это афинное любое афинное многообразие в C.
Сейчас. Тебя смущает, почему я ну как, вот, например, я хочу определить топологию на проективной кривой y в кубе равно z в кубе. Что я говорю? Что, значит, сначала у меня здесь есть открытое подмножество, там, где z не равняется нулю. Это мое u. Значит, это открытое подмножество, вот теперь я хочу на нем определить топологию. Для этого я, значит, отождествляю мое подмножество с подмножеством в длинном пространстве. Заданным уравнением x в кубе плюс y в кубе равно единице. И какая тут топология? Ну, индуцированная топология отсюда. Да, ты абсолютно прав. Я должен был написать не это, а я должен был написать, что this is equipped. Прости, пожалуйста, да. Is equipped with induced topology. Она, конечно, замкнута, но написать нужно было не это. Да. Что? Что значит точка? Нет, ну это уже топологическое пространство. Тут нет никаких c-точек. Да, это топологическое пространство просто. Good. Thank you. Да. So very good. Because they please. Okay. Now, so what else I want to say? So I have some. Let's list some properties of this functor from schemes to topological spaces. If f from x to y is proper, then I claim that the induced map is proper, which means it's closed and fibers compact. For topological spaces, it means these two conditions.
And if X and Y are reduced, then the converse also holds, right?
Right. I don't even think that for finite type things, you don't need X or Y to be reduced. So, idea of proof. Well, first, to projective F. So use Chow lemma. So Chow lemma asserts the following, that there exists a projective morphism from X prime to X such that the composition is also projective. And step 2 is well, now we have, it's using this lemma, it's easy to see, well, it's enough to show the assertion for projective morphism. Now, what is a projective morphism? It's by definition a morphism that factors through a closed embedding of the projective space, of a projective space, and the projection. So we may assume that F has this form using Chow lemma. This is my F. Now this is a closed embedding, and in this case, well, fibers at least. Well, it's the assertion is obvious, and to show it for this projection, you just use that P in analytic is compact. Okay, so and if this space is compact, then the projection is closed. Yeah, I should have said that yeah, okay. So here is another property, lemma. If F is a tuple, then F analytic is a local isomorphism, well, homeomorphism. Okay? Is it clear what it means? Okay. Proof. So the case when x and y are smooth, then the assertion follows immediately from the inverse function theorem, because the differential is an isomorphism by construction. So I want to reduce to the case of smooth y. So reduce. Okay, so first of all, may assume, okay, reduce to y equal to n, particularly smooth. Well, we may assume that x and y are fine, because it's a local statement. And then I will do the following. So I have x, which is spec well, so I want to write it as a spectrum of a polynomial algebra modulo ideal. So that corresponds to an embedding in the affine space. So here A is an algebra of polynomials in n variables over complex numbers. And so this is y, and I want to write it as, let's call it spec B. And then, by definition of a morphism, I may assume that B is a quotient. Yeah, so first of all, what I want to do, I want to
Confuse x and y.
oh, yeah, yes, thank you. Yeah. Yes. So I want to construct an embedding of this guy into something larger, and what will be the name for this larger? Okay, W, affine. It will be something affine, such that this is the top. That's the idea. And then we will show this is already smooth, so we know that this is a local homomorphism. So I want to show that Natal cover can be extended to some open neighborhood. Okay, so this will not be surjective. Yeah. So what is so we may assume that B bar is a quotient of a algebra in some number of variables, modulo some equations, Fm, with the condition that the determinant of the Jacobian matrix df bar I over dxj is invertible. Okay. So and then define define this new guy to be a spec of the following algebra. You just take take the polynomial algebra, this time over A, so, and then you mod it out by F1, comma, Fm. So what is F1, comma, Fm? I just leave this polynomial, its coefficients arbitrary. It won't work in general. But why it doesn't work? Because the determinant need not be invertible. But let's just take that's inverted. I know that it's invertible on x. Therefore, it's invertible in some neighborhood of x, and that's good enough for me. Okay, df I dxj. So then use inverse function. Theorem. Okay. So as a corollary of these two facts,
I thought that a nodal cubic has a two-sheeted cover, which is etal by two lines. So we have cxy modulo y squared minus x squared x minus 1.
yeah, yes, and so what?
It joins the square root of x minus 1.
Yeah, okay.
But then at the bottom you have a point, the node, and at this point locally your space looks like two copies of a plane glued together, and then up here it's just smooth. So that's not a local homomorphism now.
Why? So local homomorphism. No, it's not even flat. What you said. Oh no, maybe I don't understand. So here is your example. So you take this and you do this. And that's your cover.
So the lower y squared equals x squared x minus 1. That's the equation. Yeah. And then I join to this ring of functions a square root.
So this is another cubic. Okay, this is a cover. So how this cover works? So you take this copy of P1 and you sort of so what is the map from this copy of P1 to this nodal cubic? You just glue these 2 points together, right? That's your cover. Yeah, that's unramified cover. Very good. But it's local homomorphism. The normalization, though, it's not at all. It's not even flat. Okay, so we have a map. So as a corollary, we have a functor from the category of finite et al. Covers of X to finite covering spaces of X analytic. So this means just think it's disjoint union of what's called finite covers in topology, right? So I don't assume that the space is connected, but that's what you usually mean by. Okay, so we get a function. So if you have y to x and get sent to its analytification. By the first lemma, the map is proper. It has finite fibers, so it's finite. And by the second lemma, it's local homomorphism. Now, here is a really big theorem, and deep theorem, which is called, for some reason, Riemann existence theorem. So this functor is an equivalence. Okay? Okay, so I don't have, I think I have 6 minutes left, and I don't, it's not enough to prove. I'm going to prove this, only start proving this. I will prove it for smooth projective X, and I will do this tomorrow.
But your claim is the theorem is true even if I have
Yeah, yes, it's absolutely general. Amazing. So, so corollary, this corollary is what answers the question of Stepan. So if X is connected, then so is its analytification, and for any point x c, for any c point, geometric point, the induced map, the map induced by from pi 1 of pi 1 of topological of X analytic, this base point X, to pi 1 L. Is, well, first of all, what is the induced map? Well, so you have this functor. This is a subcategory of the category of all covers, right? So you have, therefore, you have a map backwards on automorphism of the fiber functors, right? Well, in fact, so what is a automorphism group of the fiber functor from this category? So we have this category. So we have a topological space. We have the category of finite étale covers of this topological space. And we have a functor, forgetful functor, well, the fiber functor that takes a cover and takes its fiber at point X. What is its fundamental, what is its automorphism group of this profinite completion? That was the first lemma that we proved in this whole discussion of the étale fundamental group. So we started with a topological group, continuous G sets, and then we show that if we restrict ourselves to finite G sets, then the automorphism of the fiber functor from this subcategory is going to be for finite completion. So that gives me a map that this is pro-finite completion. So that's kind of the Galois group, well, the fundamental group of this Galois category. And so that's a nice practice. That's the theory. Well, it's corollary of this result. Да, но есть такой. Он продолжается. Okay, so for example, so if you take P1 minus 3 points, over complex numbers, then take any base point. It's a pro-finite completion of free group into generators. Sorry. Free group. So there are no proofs of this result, which is kind of algebraic. To generators. Okay, so one last remark is that so the remark is that this topological space depends not only on X, but on the structure morphism, right? Well, because so even if X is affine, so what we do, we think of this as a quotient of a subset of affine space, and then so if I change this the structure morphism, the topological space may change. So okay. So, for example, if I take, let's do something very stupid. Let's take scheme X, and let's take some automorphism of this field. The field of complex number has one continuous automorphism, namely complex conjugation. But it has infinitely many, uncountably many discontinuous automorphisms, because first of all, you have a field of rational functions over rational numbers here, and infinitely many generators sitting there, and then you take algebraic closure, so you can take arbitrary automorphism of this field of rational functions and then extend it. So let's take some automorphism. Okay? So let's call it sigma. Then you can you can view X, this scheme X, as a scheme over C in two different ways. Right? So if you kind of used to think about this in terms of equations, well, think of X as given by equations in some affine space in Cn, and then just apply this automorphism sigma to the coefficients of this equation. Your automorphism is not continuous, so the manifold given by this topological space given by these new equations has absolutely nothing to do with the original. So you have X analytic, and in general, it's not isomorphic to X sigma analytic. Though well, X analytic C, well, is the same as X sigma C. Is it clear what I mean here? So you have a bijection between sets of solutions of two systems of equations. Namely, if you have one solution, you apply your sigma to each coordinate. And you get solution to another system, right? But this map is not continuous. Moreover, Serre constructed an example of smooth projective X over a number field such that if you consider this X as a topological space in two different ways, so and two embeddings of K inter complex numbers, right? You have as many embeddings as the degree. So I1 and I2 such that the fundamental groups of the corresponding spaces, pi1 topological of X Ki1 C analytic is not isomorphic as an abstract group to pi1 topological X K I2. Right? So in order to define a topological space, you have a variety given by equations with coefficients in K, and I want to associate it with topological space. What I have to do, I have to choose an embedding of this field, interfield of complex numbers. So a priori, if I choose two different embeddings, I get different even topological spaces. But in fact, even the fundamental groups could be different. But they are profinite completion. Completion must be isomorphic. Why? By Riemann existence theorem, because they are these two schemes abstractly isomorphic. The isomorphism is not C-linear, but it doesn't. We do not care. So pi1 is kind of does not depend on the structure morphism to C. Pi1 et al. Fine completions are isomorphic. Okay. So I have to stop here. Thank you. Questions?
Yeah, I have a question about this corollary, this connector. So if X is proper, then the proof goes on as follows. Assume X analytic is disconnected.
Then it's not a Golok category.
No, I want to sort of, I describe the details. So, then you can decompose the structure as a direct sum of two ideals, but then by Serre's theorem, there is an equivalence of categories between here and sheaves there and there, so the OX also decomposes, therefore X is disconnected. So do you, sort of, if X is not proper, do you have a way to reduce those to the case?
Yeah, it's easier. It's so this proof of connectedness. Well, the one that I thought about still uses reduction to the proper case and some Hartog's a theorem in complex analysis, which is called the Hartog's theorem, that asserts that holomorphic functions cannot have singularities in codimension 2. Right, so you use this to show that every meromorphic function on the projective space is rational, then every meromorphic function on the projective variety is rational, and then you reduce to projective case essentially by showing that if you have a analytic idempotent, then it's a bounded function, so it extends to compactification, to bounded function compactification.
But then you need some sort of smoothness assumptions.
Yeah, so and first you need kind of to.
So it relies on
yeah.
suspicionless form of resolution.
Well, no, there is a simpler, that's kind of the shortest proof, but there is a self-contained proof which doesn't use deep results as resolution of singularities, but it's long, and it's explained in the book by Mumford, Complex Projective Varieties. It takes maybe 10 pages.
And do the proof of
Yes.
reduce from
Yes.
like if you just compactify them, the fundamental groups which change.
It's changed in a controllable way. So, if you, this we'll also discuss. So if you have like a normal variety, then you can compare the fundamental group of your variety and the fundamental group of the generic point. And the fundamental group of variety is a quotient of the fundamental group of the generic point. And if you kind of change your variety, smooth variety in codimension 2, then the fundamental group does not change at all. But yeah, you're right that that's yeah, you can. It's not enough, so you have to really kind of talk about ramifications. So it's and I will not explain this part. I will only explain the smooth proper part, which is still relies on some deep theorems in complex analytic geometry. Identification of X and
Except sigma.
oh yeah, sure. So in fact, so you may think how these two examples are related. So these two varieties over C are obtained by this twist, and they are smooth projective.
The theory description of the corresponding fluids relations on complex fields.
No. I mean, from point of view of complex geometry, it's very kind of ridiculous idea to apply a non-continuous automorphism of C. Yeah, so okay. Да. Ага.
Знаете ли вы пример таких иксов, когда x и x будут иметь разные геометрические типы?
Подожди, вот тут просто P1 разные.
Нет. Это же два разных.
Это абсолютно то же самое. Вот просто возьмите вот это, любые два таких вложения отличаются на автоморфизм сигма. Примите этот автоморфизм к этому многообразию, получится это. Да, простите, на автоморфизм С. Нет, ну что значит? Вот я утверждаю, что вот. Да какой-то автоморфизм, да, сигма. Вот возьмите это многообразие и примените, значит, рассмотрите его как комплексное многообразие с помощью первого вложения. Потом выберите такое сигма, которое и1 переводит в и2, и примените вот ту конструкцию. Получится второе многообразие.
Там же мы взяли очень конкретное сигма.
Какое? Любое.
Сопряжение.
Нет, любое. Если сопряжение, то эти многообразия — это единственный случай, когда эти многообразия просто гомеоморфны, потому что комплексное сопряжение будет непрерывным. Если вы возьмете систему уравнений и сопряжете коэффициенты, то, конечно, множество решений тоже будут, естественно, будут гомеоморфизмы.